Let's discuss about Ampere's law. Quick discussion on this. Now, we have just seen, okay, that we can actually find out the magnetic field using the Biot-Savart's law. So, if we want to find out a magnetic field due to a very small current carrying element, we can use the Biot-Savart's law like this: IDL sine theta by r square. So, whatever forms we have seen, special cases we have seen everywhere, we used Biot-Savart's law. Just like Gauss's law, if you remember, Gauss's law, what we did was we created a Gaussian surface, an imaginary surface, okay, and from there we were able to find out what was our electric field, okay. So whenever we talked about Gauss's law, we saw that if we are talking about the electric flux, which is nothing but E dot A, is nothing but the total charge enclosed divided by epsilon naught. So this is the total charge that is getting enclosed. In this particular case, when we talk about Biot-Savart's law, we are actually finding out the magnetic field due to a small current carrying element. So Gauss's law and Ampere's law are something similar, where we are basically going to consider a imaginary surface again, okay? And here we are going to use Ampere's law. For example, let's say we have got a current carrying conductor I, and we want to find out what is the magnetic field at this particular point P. So we can obviously use Biot-Savart's law. No harm in that. But there are certain situations where Ampere's law will give me the result quicker. Okay, it's not that everywhere you can use Ampere's law or everywhere you can use Biot-Savart's law. Although the book mentions, but when we're using laws, it is meant to make things easier, not complicated. So Ampere's law can be used everywhere. Wherever there is a current flowing, I can create a loop, I can create an imaginary surface and find out the magnetic field. But for certain system, okay, where charges is flowing, the law becomes more complicated. Although we can use Biot-Savart's law there, okay. So it depends on what situation you are considering, and based on that, we can actually use the Ampere's law, Biot-Savart's law. So if you're basically considering a current carrying conductor, and I want to find out the magnetic field at a particular point P, what we can do is we can actually use this Ampere's law. This Ampere's law will also give me the direction as well if we use the thumb rule, not a problem. Okay. So this is a 3D image. Imagine this is the loop, the current carrying conductor, and this is the loop that is getting formed. Now look at this loop from the top. So if you look from the top, you are going to see a circle, which is actually called the Amperian loop, and the current is coming out. We're looking it from the top. Okay. So if you're looking it from here, so if you're looking it from the top, you're going to see that it is going to form a loop and there is a current which is coming out. Okay. We know if we are drawing this, making a dot, it is coming out, making a cross, it is going in. Okay. So this loop that we actually have is called the Amperian loop, just like Gaussian surface. Okay. Or Amperian surface also we can write it down. Okay. So in a way we can actually use this, and Ampere's law states that the total magnetic field for a closed loop, again here also we are talking about closed loop, we are going to find out the closed loop, and let's say this is dl is equal to mu naught into I. Okay. So we have to know what is the angle, right? This is dot product, so this is cos. Okay. And the angle between the field and the uh, you know the loop's small region. Okay. So if you look into the field here, you'll see that if you're going to use the right hand thumb rule, okay, this is going to uh, if you just check here in this particular case, okay, the current is going up. So on this side it is going to come out of the plane of the paper, and this side it is going to go into the plane of the paper, right? This is going to go into the plane of the paper, and this is my dl. Okay. So if you are going to find out maybe the angle, okay, and if you're going to find out what will be the field at any point P, we can consider that angle, and based on that we can actually do our calculation. So if it is, this is an entire loop, let's say the magnetic field is B and we are going to find it out as dl. It is nothing but mu naught into I, and let's say uh, I can. It's not that I have to find it here. I can find it out at any point. Okay, you have to just make that loop. Okay, at that particular point. So if you're considering this, and let's say this loop is having a radius of a, I can simply write down what is the entire length. That would be 2 pi a is equal to mu naught I. Right. So that means my magnetic field is mu naught I divided by 2 pi a. Okay. So that's my magnetic field due to this loop. We can consider different cases. For example, let me just consider a cylinder. Okay, this is a cylinder, and cylinder means it will just look like a wire, and there is current flowing in this, but the current that we have is only at the edges. Let's say this side we have got I, this side also. Okay, I1, I2, and so on. Or maybe only at the edges we have current, which is I. Now the question is, just like we did it for circular coil, we have to find out the magnetic field at a point P, which is inside, and let's say I have to find out the magnetic field at a point Q, which is outside. And let's say the radius of this is capital R. The radius of this is capital R. So what we can do now is we can actually look it from the top, and we can make a loop. Let's do it from inside, for inside. Okay, if we do it for inside, we are going to see that we can actually make a loop, and this would be the inside one R, and the radius of the coil is larger R. This is my radius of, of the coil, it's capital R. The current is flowing in the larger coil. This is my I. Okay, so if you were just want to find out what is the magnetic field, we can easily use the Ampere circuital law. B dot dl is equal to mu naught into I. Okay, so angle between B and dl is 0 degree, so cos 0 is 1. Okay, so we can simply write it down as B integration of dl is equal to mu naught I. Okay, so please remember, or please understand this, that this I that we are considering is nothing but the current that is enclosed or inside. Okay, so this is the current which is inside, so that means inside the loop. Okay, so if you are considering this, this is current inside loop. So if you check this, this is my R, and the current is flowing here. So that means if you are considering this loop, this is my loop here, it does not enclose any current. Okay, therefore we can simply say that P is equal to 0. It's very simple. It is something like we have a conductor and we are having the current flowing outside. We are not going to get any kind of field inside. In magnetic field also, if you are considering the Ampere's law, we have got the current flowing inside. There is going to be no magnetic field. Okay. So that's important. So this is my magnetic field inside. Let's just have a look at outside. So this was the case when this R was actually less than capital R. That means inside the system. Okay. But if we are considering R as greater than capital R, that means we have the current like this I, and the larger loop is here. This is my Amperian loop, right? Now this is my loop. Okay. So this was the cube. So this one is capital R now, and this is my small r. Now in this case, it's simple. We can simply write it down as B dl is equal to mu naught I. I is inside, and inside I'm saying that the current is I. So this will actually enclose the current. So that will give me a result. So B is equal to mu naught I divided by integration of dl. This entire loop, the radius is r. So I can simply write it down as 2 pi r. Now what we observe here is that In the previous case, when we are talking about finding out the current or the magnetic field at a point P, due to this current carrying wire, we found out the result to be mu naught I by 2 pi a, where a is the radius. You see that the result remains the same. I'm using R here, we can use A. The result remains the same. That means even if you are considering a current carrying cylinder, the magnetic field will be the same. It will just add up all the current and then it will give you the same result. So this is a very important conclusion. Okay, so if you are considering this inside, it is 0, and if you are considering it outside, we are going to have this result. Okay, so this is important. So you can have different kinds of questions in these kind of problems. Okay, this topic we can have different kinds of questions. Let's say I'm having a cylinder where we are having so much current. It's an uniform distribution of current. Okay, like this. We are having these current. Now this time, it's not that inside there is no current. Even inside also there will be some current. Okay, so if you consider that, uh, and if you want to find out what is the, let's say, magnetic field at this particular point P, which is inside, and I want to find out what is the magnetic field at this Q, which is outside. Okay, I have to take an approach where I consider what is the current density. So this is I. Okay, and if you want to find out what is the current density, we should know this concept. Current density, we know J is equal to I divided by area. So if I want to find out what is the current here, we should know what is the total current and divide by the area that we are actually considering for finding out the current density. Okay, so in this case, B inside is not going to be 0, because this is going to enclose some current, right? And even B outside is obviously not going to be 0. Okay, so current density, we already know what is this, right? So please remember, this logic that we are going to use here is for uniform distribution of charge. That means the current density will remain same whichever part you consider. Uniform distribution of charge. So what was our formula? Our formula was BdL is equal to mu naught I inside. So if you are considering, let's say, for R less than capital R, let's say this is my cylinder where the current is there, and this radius is capital R. We are considering a point inside. So let's say this is my small r. So we can simply write it down as mu naught into, now what is I? If you look here, I is equal to J into area. Okay, J into area. So this area means we are talking about the current density. That means we are going to consider the entire area here. Okay, if you are going to find out density, you know, let's say it is mass by volume. That means if you want to find out what is the mass, it is nothing but density into volume. Which volume? Whichever volume you are considering. Similarly, if you are considering current density as I divided by A, for the entire cylinder, this is my current density. I divided by pi capital R square. So the question is, what is the current that is there in this particular loop? So in that particular loop, it would be nothing but whatever is the current density into pi small r square, because we are interested in finding out what is the current in this particular loop, or what is the current that is being enclosed by this loop. So the current enclosed by this loop is nothing but the current density multiplied by the area of this loop. Okay, so that's the mistake that we've done. And what is J? J is current density. Current density is nothing but I divided by pi capital R square. Now this is okay. Into pi R square. Because if you look into the Ampere's law, this current is nothing but the current that is enclosed in here. So if I write down capital R square, I'm talking about the entire current. But no, this is the enclosed current. So enclosed current is J into pi r square, density into whatever is the area that we are considering getting enclosed. So now I think it's fine. We can do our cancellation. So this is 2 pi r. Uh, so this is 2 pi r. So let me just simplify things here. This pi and this pi will actually get cancelled out. So I can write it down as mu naught I into r square divided by uh, pi r square. So pi we have cancelled out. This is capital R square into uh, 2 pi r. That was 2 pi r. So pi pi gets cancelled. This is okay. That's fine. So this and this will actually get cancelled. So I'll simply have it as mu naught I r divided by 2 pi r square. Okay. So this would be the result for this. So we can use this result, and we can actually even draw a graph for this particular system. Okay, inside and outside. Okay, because if you know, if you look into outside, if we just want to find out the outside part, okay, here what we do observe is that this magnetic field that we are considering is directly proportional to r. Okay, so as r increases, the magnetic field will also increase. Okay, now if you want to look into outside, this is actually simple, because the current that is there inside will remain the same, right? So if we are considering it outside, we know that if we are considering this cylinder, the total current is I. The total current is I. So if you're considering a point P here, we can actually draw a loop, and this is enclosing a current I. So here I don't need the concept of current density. I can simply write it down as B is equal to mu naught I divided by dl, which was nothing but 2 pi, whatever is the loop, this R. So here I don't need to know the current density, because I know that the current that this entire Amperian loop encloses is I. But inside we need to know the current density, because I need to know how much current was here. So only that much is considered in the Ampere's law. So this is mu naught I by 2 pi r. Okay. So here also we can actually construct a graph where we can actually take the magnetic field along the y-axis, and the distance along the y-axis. This is the distance r, and this is my magnetic field b. So if you are basically considering the loop here, okay, this is the border. Inside, if you look here, if you look inside, it is proportional to r. Okay, check here, proportional to r. And if you're going to look outside, okay, if you're going to look outside, this is proportional to 1 by r, proportional to 1 by r, right here. E is proportional to 1 by r. So if it is inside, it is proportional to r. That means the magnetic field is going to increase with distance. But when we are coming outside, it is inversely proportional to r. So inversely proportional to 1 by r. This is proportional to r. This is how you can actually construct the graph for this. Similarly, in this case also we can actually construct the graph. We didn't do that. Let's just do it first. So here also the same thing. If you're basically considering r and the magnetic field here, okay, still this r is equal to capital R. If you're considering it inside, it is 0. So this is 0. This is 0. At the border, there would be a jump. Okay, there would be a jump, and then again it falls 1 by r. So it is again going to be like this. So the graph will also change depending on whether we are having a distribution of charge, or the charges are only flowing across the surface. So that's very important, which is actually called as the Amperian loop. Okay, so as you can see, the formula is pretty simple. It all depends on what is the geometry here. Okay, what kind of Amperian loop you are usually considering. So B dot dl integration is equal to mu naught I. will be the main relation, where current is basically nothing but the enclosed current in the Amperian loop. We have seen different kinds of problems. For today, what we are going to see is we are going to talk about solenoid. Okay? Solenoid is also an important part. Uh, it's there in the syllabus separately as well. Okay, as you can see. So we do have something which we call as solenoid. So what is a solenoid? Solenoid is, it's a coil kind of structure that will usually, carry current. And if it is carrying current, definitely there is going to be some kind of magnetic field that it produces. Okay. So a solenoid is usually, structured like this. You basically have an insulator at the center. Okay, and mostly this insulator may be a cardboard or something like that. Okay, it's a cardboard maybe, let's say, so that the wires are there, which doesn't collapse, and the wires are actually in this rotation. So we have the coils in this cardboard coiled around, and what happens is this solenoid, if you actually want to pass a current, is actually connected with a circuit. So you can basically have a circuit like this, maybe connect a battery, and you basically having a current flowing in this solenoid. Interesting part of the solenoid is that if you allow the solenoid to hang freely, it is going to point in the north south direction. Okay, so what else shows that behavior? A compass. Okay, or a magnet. So whenever you have a magnet and you are hanging it freely, its direction is fixed, it's going to be in the north south direction. Okay, that is something which we already know because of the magnetic field, earth's magnetic field. So here also, if you are taking a solenoid, you are hanging it freely and it is pointing in the north south direction, it obviously means that this solenoid is also generating a magnetic field. So it is another way to say that a current carrying conductor will definitely generate a magnetic field. Okay, so that's a very interesting observation. But when you're basically considering a solenoid, most of the times, okay, we are basically considering it to be an ideal solenoid. Okay, an ideal solenoid. So what happens is an ideal solenoid will basically have a uniform magnetic field inside, and magnetic field outside will be zero. So in an ideal solenoid, that is a very important definition. The magnetic field outside is equal to zero. That's the first observation that is important. Okay, and the magnetic field lines, as you know, it's a solenoid, so definitely is going to have the field lines. The magnetic field lines, they are basically straight. We'll draw the field lines now. Okay, and parallel to the x-axis. Okay, parallel to x-axis, we can say. You can have objective questions based on this, right? And uniform in nature. They are uniform in nature, so that means we don't have a field lines which will basically be too much separated or too much close. Okay, they're uniformly distributed in nature, let's say. Number three, the length of the solenoid. This is the length of the solenoid. Okay, this is the length of the solenoid, very important. And this is the radius of the solenoid, let's say r. But the length of the solenoid is always very large compared to the radius of the solenoid. Okay, and then finally, if you are having an ideal solenoid, then n, okay, it is very very large, very large. Okay, what is n? N is number of turns per unit length. Okay, so this has to be very large when we're basically considering an ideal solenoid, and that's important. Whenever we are considering a solenoid, So the question is, what will be the magnetic field inside the solenoid? Before that, how does the magnetic field look inside a solenoid? So you're basically having a solenoid like this. You are having the coil like this, and if you are passing a current, you are going to get a magnetic field which should be parallel to the x-axis. So exactly at the center, imagine this is a three-dimensional picture. Okay, so that means if you are looking into it parallel, it is going to show some curve. If you're looking it from the side, it's going to be something like this. The magnetic field is going to be something like this. So this is the direction of the field. Obviously it will be this direction or the other direction. It will depend on, what is the flow of current. Okay, so these are my field lines. So that is how it looks. No field lines outside, that means it's basically going to form a loop inside. Okay, it's there is no field lines here. Okay, so there is no field lines here, so there is no field outside, the field is only inside when we're basically considering a ideal solenoid. Okay, so that was, a very basic idea of the solenoid. Now you can take a cross section of the solenoid and basically cut it and try to find out what is the magnetic field inside an ideal solenoid. And for this, what we are going to do is we are going to use the Ampere's law. So very simple idea: magnetic field inside an ideal solenoid. And if you're considering an ideal solenoid, we know that this has to be long, so it is infinite, in the sense that the length of this solenoid is much much large compared to the radius of the solenoid. Okay, so that is what is infinitely long means here. So we can actually do it, and we can actually use the Ampere's law to find the field. For that, what we can say is that, let's say I'm having my solenoid like this. Okay, and of course there are field lines here. Okay, so there are field lines. So these field lines are uniformly distributed, as I said. So I'm basically, yeah, having the field lines something like this. The direction of the field line is again given by this right and thumb rule. We can test it. And let's say this is uniform. Although my drawing doesn't say it's uniform, but these lines are very uniformly distributed. That means they are at equal distances from each other. Now I want to use Ampere circuital law to find the magnetic field. Okay, so for that, what I can do is I can simply consider a small part of this. Let's consider this is my Amperian loop. Okay, so this is my Amperian loop. So if I have an Amperian loop, and we'll definitely, we need to find out what is the current in this loop. So first thing, what is the Ampere's law? Okay, so our Ampere's law is B dot BL is equal to mu naught I inside, whatever is the current that is being enclosed. Okay, and we can see that there is a loop here, Amperian loop. So let's mark this loop as A, B, C, D. Okay, so we need the direction of the magnetic field and the direction of the length that we are considering, so that we can find out what is the mu naught I value, right? So if you are considering this loop, that means the loop is A, B, C, D. Okay, so if you remember a bit of integration here, what we can do here is like this. We can write down this integration, this part of the integration, as this integration B dot dl AB. We are going from A to B, B to C, C to D, D to A, so that we are forming a closed loop, right? So in integration, we can actually do it, do it like this if it's a closed integration, and then we are going from B to C, again B dot dl. So it's a dot product. That means we are talking about the cost function, right? and then we have got CD, which is B dot dl, dA B dot. This is equal to mu naught I inside, right? So first thing, B dot dl. B dot dl is AB. AB is outside, we can see it is outside, and it's an ideal solenoid, so there is no magnetic field outside. So it is not enclosing any magnetic field outside. So that means this term, okay, has to be zero. This term has to be zero. Next, B dot dl BC. BC. So you see the length, if you're considering the length, this is dl in this direction, but the magnetic field is in this direction. Okay, so that means B dot dc dot product, so it is cos, which is cos 90, and cos 90 is equal to 0. So that means there is no magnetic field because of this as well. What about CD? CD, actually it's there, right? So you can see, if you're considering the length in this direction or in the other direction as well, okay, dl, this is the length, and this is the direction of the magnetic field. It is making an angle of 180 degree, so obviously it's not 0, right? -1, so this is not 0. So that means this will actually contribute to the magnetic field that we're going to find out. And finally this dl, the same logic as bc, da, okay, this is in this direction, again making an angle of 90 degree. So for this case also, we are basically having it as cos 90 degree, which is equal to 0. So finally, I have to just find out what is the magnetic field because of this line, right? So what we can do now is, we can just simply take up this result, B dot dl, okay. So let me just write it down, CD. So I'll take it CD, okay, that's my only case which survives. B dl, let's say this is cos of 180 degree, although the magnitude does not is more important rather than the sine mu naught into I. So this is minus b, we can take it out. Dl is equal to mu naught I, right? Cos 80 is -1, so I've written it like this. So that means b into L. This is a small length dl. I'm considering a small length dl. If I'm considering the entire length, let's say the each side is of length L. So if I'm considering the entire length, this would be BL is equal to mu naught I. Okay. So this is the first thing that we should know. Okay. Now, what is our N? Okay, we just discussed that in the previous slide. If we talk about what is our N, N is actually nothing but number of turns per unit length. So maybe we are having a length of 1 meter or centimeter or foot or whatever. In this 1 unit, there will be n turns, n number of turns. Okay. Now how many turns we have? We have got, sorry, what is our length here? L. So our length is L. So that means in L length, L meter or L centimeter, the number of turns would be n into L. N into L turns. Okay. This is normal unitary method. In 1 centimeter, n turns. In L centimeter, n into L turns. Right. Similarly, if you're talking about in one turn, the current is I. Let's say I is the current. Okay, in one turn, I is the current. How many turns we are considering here? For I, we are guessing taking length L. So that means there are NL number of turns. So NL turns, the current is nothing but NL into I. Current. So you can see here that in one turn there is I current, in NL turns it will be NL into I current, right? So we are talking about a length L, In length L, there are NL number of turns. So that means the current that is there is nothing but NL into I. So that means what I can do is, if I just take the magnitude of the magnetic field, I'm just considering the magnitude. That's why I've dropped the minus sign. Okay, so don't get confused. This is equal to mu naught into I. But I inside is nothing but in L length. In L length, there are NL turns, so current is NLI, right? So I can simply write it down as NLI. Works more with logic, so this L gets cancelled here. So that means the magnetic field due to a solenoid is mu naught N. Okay, so what we are doing here is we are using the same Ampere's law, and using the Ampere's law, we are finding out what is the magnetic field. So if we are having the topic of solenoid in this chapter, so this is something which we should know. Okay, first thing, what is a solenoid? What makes it an ideal solenoid? And then, of course, what is the magnetic field? We can use the